Now, let us find a formal expression for the inversion of the Z transform. As with the Laplace transform, we start the process of deriving an expression for the inversion of the Z transform using the fact that the the Z transform is the DTFT of the modified sequence. That is to say that x z is the DTFT of x n r to the minus n. Keeping this in mind, we can write that the inverse DTFT of x z is x n r to the minus n. So, you can write, we have an expression for the inverse DTFT of any sequence. We can write the inverse DTFT of x n of x z is r to the x n r to the minus n equals 1 by 2 pi integral minus pi to pi x z e to the j omega d omega. The integration is done here over values of omega from minus pi to pi, which is to say the path of integration is the unit circle in the z plane. Fine, because on the unit circle we do know that this converges for whatever value of R n, this does converge. It is only when that is the case that this expression, this entire expression is meaningful, all right. So, okay. Now, what we will say next is this: if the integration path is the unit circle on the z plane for this expression, let us continue to see what happens if we multiply both sides by r to the n, so that we just get x n. X n equals 1 by 2 pi integral minus pi to pi x z r to the n e to the j omega n d omega. This is just equal to z to the n, as you can see. Finally, we need to change variables. We need to change variables a little. We have to use z equal to r e to the j omega. So, dz by d omega equals r e to the j omega by j That is to say that dz by jz equals d omega. If you make this substitution, then the variable of integration is z, and therefore, the path of integration has to be through the ROC. So, taking a path through the ROC, integration path within the ROC, xn becomes equal to 1 by 2 pi j integral r e to the j minus pi to r e to the j pi x z z to the power n minus 1, because we have a 1 by z over here, dz. So, this is the formal expression for the z transform inversion. Though we have this formal expression for the inversion, we shall not, just as with the Laplace transform, use it very often. Since our concern will largely be with exponential functions and a few other standard forms for which the Laplace transform, the Z transform inversion is given by a familiar formula, we do not really have to do this integration. So, let us see what we really need to do if we have a polynomial rational form, which is the usual thing that we get when we start with a difference equation describing a system, that we apply the Z transform to on both sides and then get an expression for H Z. So, what we will have is a polynomial rational form. For inversion of polynomial rational forms, inversion of polynomial rational forms, what we have to do is to do a partial fractions expansion to obtain smaller terms, smaller and more familiar. Now, second, assign forward smaller familiar terms that can be inverted. Assign to each component term an ROC such that the combined ROC of the component terms matches the ROC given for the overall expression. In order to do this, you will have to recognize a simple fact that was reasonably apparent in the examples that we have worked out so far. That is that the ROC is bounded by the existence of poles. By recognizing that the ROC is bounded by a pole, if the elementary term that we invert has one pole, as is usually the case, then there are only two choices for its ROC. There are only two choices for its ROC. So, if you have n terms, n component terms, there are 2 to the n ROC combinations and the right one is chosen by checking for a match with the given ROC for the overall expression. So, that is what we have to do. Now, let us go through a list of standard Z transform pairs, common Z transform pairs, which are likely to occur as the component terms. We are already familiar with two of them. A to the n un transforms to 1 by 1 minus a z inverse with an ROC of r greater than a, minus a to the n u minus n minus 1 transforms to the same thing, 1 minus a z inverse r less than a. Then there are some more expressions which we will just note down. N times a to the n un transforms to a z inverse divided by 1 minus a z inverse whole squared with an ROC of r greater than a. This comes out from the differentiation in frequency property, which we will discuss later for the Z transform. Then you have minus n a to the n u minus n minus 1, which also transforms to the same expression, a z inverse by 1 minus a z inverse whole squared. but this for r less than a. Fine. So this is a typical expression you get when you differentiate in frequency, differentiate with respect to z. Next you have a to the n sine cos omega naught n u n, which transforms to 1 minus a cos omega naught z inverse, 1 minus a cos omega naught z inverse over 1 minus 2a cos omega naught z inverse, 1 minus 2a cos omega naught z inverse plus r squared by plus a squared by z squared for r greater than a, that is the ROC. Finally, you have a to the n sine omega naught n un, which transforms to 1 minus there is no 1 minus, you just have a sine omega naught z inverse over 1 minus 2a cos omega naught z inverse plus a squared by z squared with r greater than a as the ROC. So, these are some of the standard forms. Now, the last two forms that we have over here, namely that corresponding to cos omega naught n and sin omega naught n with an exponential term like a n attached multiplied, will simplify appropriately to the case when a is taken as 1. For example, the first expression a n cos omega naught n u n will just become cos omega naught n u n, an oscillatory function, and that will have a z transform, as you can evaluate from this expression, as 1 minus cos omega naught z inverse by 1 minus 2 cos omega naught z inverse plus 1 by z squared. All right. So, these are the standard forms. One needn't worry beyond the standard forms. Now, I will work out an example in detail to demonstrate how, if you have a certain h z given to you, or x z, whatever you want to call it, and you are given the task of inverting it by using partial fractions expansion and identification of individual ROCs, and then inversion of the individual terms. So, let us try to do it for a concrete example to make us more confident about it. Before we do this, it is convenient and in fact essential to learn some of the standard properties of the ROC of the Z transform. These properties will very closely resemble the properties of the ROC of the Laplace transform, and so we will go through them in more or less the same order and point out the analogies where as and where we meet them. So, properties of the ROC of the Z transform. Okay. The first property, analogous to the first property we discussed there, is that the Z transform, the ROC of the Z transform, the ROC of the Z transform consists of complete circles. In the case of the Laplace transform, we found that it consisted of complete vertical lines. Well, the reason here is similar to the reason over there. This is because the Z transform of Xn is the dTft of Xn r to the minus n. So, if the Zt of Xn exists, it means that Xn r to the minus n is absolutely summable. Right. If it is absolutely summable, then you see that absolute summability has nothing to do with omega. It has only got to do with r. So, absolute summability of Xn r to the minus n is visibly independent of omega. Hence, Xn r to the minus n will be summable Xn r to the minus n e to the minus j omega n will be summable if it will be summable for all omega in 0 to 2 pi if it is so for any particular omega. That completes the proof, so to speak. The next thing, of course, the next familiar statement we make, the next property of the ROC of the Z transform is that the ROC by its very definition is a region of convergence, and so it cannot contain any poles. The ROC cannot contain any poles. Now, the third property. Suppose we have Xn as a finite support sequence, a sequence which just runs from say some n a to n b. Let Xn have a finite support. Then we have, let the support be say n a comma n b. That is to say that xn equals 0 for n less than na and n greater than nb. This is what we have. Then clearly xn will always be absolutely summable. So also will be xn r to the minus n, correct. Xn r to the minus n will also be absolutely summable, because r to the minus n a, r to the minus n b and r to the minus n for n a less than n less than n b are all finite. For any r, for any finite r. Hence, the ROC is the complete finite Z plane. However, there is a proviso, there is a caveat. If n a is less than 0, then x z will contain a term such as x n a z to the power minus n a. Fine. Now, since n a is negative, z to the power minus n a is just equal to z to the power mod n a. And this will not converge at mod z equal to infinity. Remember that unlike the Laplace transforms context, here we include infinity as part of the z plane as well as the origin z equal to 0 as part of the z plane. So, this means that this has to be taken note of. The finite z plane is completely covered, is completely part of the ROC, but z equal to infinity is not part of the ROC. Likewise, if n b is greater than 0, x z will contain x n b z to the power minus n b, where n b is greater than 0. So, you have 1 by z to the power mod n b, x n b times 1 by z to the power mod n b, which will not converge at mod z equal to 0. Thus, summarizing, thus for a finite sequence, Thus, for xn with finite support, the ROC is all of the z plane, the z plane excepting either z equal to 0 or z equal to infinity or both. So, that is for the finite length sequence, finite support sequence. Now, let us look at the next case, next property of one sided sequences. We will handle both the left and right sided sequences at one go by writing that if xn is right parenthesis left sided and the ROC of x z contains the point z naught equals r naught e to the j omega naught, then it will also include all points z satisfying mod z greater than mod z naught, in parenthesis mod z less than mod z naught. Now, this is proved by a process that is extremely analogous to similar proofs for the Laplace transform case. So, we will not bother to go into this further. All we need to point out is, by making this combined statement for the left and right sided sequences, we are saying that these are actually two statements. If xn is right sided and the ROC of xz contains z naught, then it will also contain all points of z satisfying mod z greater than mod z naught. The second statement would be, if xn is left sided and the ROC contains the z point z naught, then it will also include all points z satisfying mod z less than mod z naught. So, these two statements are being made together. In addition, there is the caveat that came up with the previous case. If xn is right sided but starts at n a less than 0, then z equal to infinity will be excluded from the ROC. Likewise, if xn is left sided but ends at NB greater than 0, then z equal to 0 is excluded from the ROC, right. So, this is just the application of the same arguments that we found for the finite support sequence case. Finally, we have the case of a two-sided signal. Fine. Now, for two-sided signals, they are split expressed as a sum of a left sided and a right sided signal. You may express it as a sum of a left sided and a right sided signal, all right. Then we apply the two criteria that came out of the previous condition for one sided sequences simultaneously, and we have an ROC for one sequence, for one part of the sequence, and ROC for the second part of the sequence, and we know then that the ROC for the combination will be the intersection of the component ROCs. The ROC for the complete signal will be the intersection of the ROC of the complete signal will be the ROC of the will be the intersection of the component ROCs. ROCs, if they both exist, and intersect. Fine, that is for the two sided thing. So, let us summarize what we have found. For finite support, Xn, ROC is all of the z plane except possibly z equal to 0, z equal to infinity, or both. For one sided sequences, for left sided sequences, the ROC extends inward indefinitely. And is bounded outside by a pole. We call such a configuration an inward ROC. Inward ROC, and it happens for left sided signals. Next, for right sided signals, signals. The ROC extends rightward or rather outward indefinitely, and is bounded inside by a pole. Thus, the outward ROC is what you call this, and it corresponds to right sided sequences. Right sided sequences. Fine. So, it is very nice. Inward ROC for left sided signals, outward ROC for right sided signals. Of course, with in both cases we will have to say that z equal to 0, z equal to infinity may appropriately be excluded. In both cases z equal to 0, z equal to infinity may appropriately be excluded. Finally, for a two-sided signal, the ROC is bounded both inside and outside by poles. Hence, it is in the form of an annulus. However, if the sequence xn begins to grow both in the direction of n greater than 0 and n less than 0, the intersection of the component ROCs will be null, and we will say that xn does not possess a Z transform. So, let us stop at this point and continue the discussion in the next session. So, let us work out an example that brings out many of the features of the manner in which we solve the Z transform, the way we invert the Z transform. So, here is the example. Let x z be given by 2 z squared minus 7 z over x z squared minus 7 z plus 10. This is a sufficiently cryptic looking x z, and let us say that the ROC R is given as follows: 2 less than R less than 5. So, this is an annular ROC. Now, from our knowledge of the properties of the Z transform that we of the Z transform ROC that we have just acquired, this seems to suggest right on the face of it that we have a two-sided signal, because the ROC is annular. Okay. The first task is to do a partial fractions expansion. Now, if we carry out a partial fractions expansion, it turns out that this is equal to z by z minus 2 plus z by z minus 5. This is what we have, which can be written in the more familiar form as 1 by 1 minus 2 z inverse plus 1 by 1 minus 5 z inverse. So, we have this. Now, is the real task of choosing appropriate ROCs for each of these two component terms, components of the partial fractions expansion. Okay. Now, consider 1 by 1 minus 2 z inverse. This can either represent a leftward ROC with R less than 2 or a rightward ROC with R greater than 2. It can't be any third possibility, because we have 2 as a pole in the function. So, let us look at the ROC of the complete function. Let us make a plot of the ROC of the complete function. Let us make the unit circle. Then you have 2, this is at 2, this was at 1, this is at 2. And then there is the third boundary at 5. You have the third boundary at 5. We are told that the ROC is annular. That means to say that the ROC fills up the space between these two dotted boundaries that we have drawn, like this. This is the annular ROC we have, that is the ROC. Now, the ROC is bounded inward at 2, inside at 2 and outside at 5. Such an ROC can only be found as the intersection of an outward ROC starting from 2 and an inward ROC ending at 5. So, that is the comment we have to make. Now, an ROC of the kind shown can only be the intersection of an outward ROC bounded inside by mod z equal to 2 and an inward ROC bounded outside by mod z equal to 5. That is the only way you can do it, right. So, when this is clear to us, we have to only assign the appropriate ROC to the appropriate term. The first term over here, has a pole at z equal to 2. Okay. This second term over here has a pole at z equal to 5. This means simply that it is the first term that should have an ROC which is outward and it is the second term that should have an ROC which is inward. So, now we are in a position to completely separate the two terms and assign them their respective ROCs. We will say therefore, that x1 z equals 1 by 1 minus 2 z inverse with r greater than 2, x2 z equals 1 by minus 1 minus 5 z inverse with r less than 2. Now, what does this transform to? The inverse transform of this will be, this is an outward ROC. An outward ROC will have a signal which is right sided. So, the right sided signal for a form which is a standard form such as this will simply be 2 to the n un. And similarly, for this expression which is 1 minus 5 z 1 by 1 minus 5 z inverse, which has an inward ROC, it will be of the form minus 5 to the n u minus n minus 1. So, adding the two terms together, we can write that xn, which is the inverse transform of the complete xz that was given to us, is 2 to the n un plus, or rather minus 5 to the n u minus n minus 1. This is the complete exercise of inversion. But let us just explore other possibilities that could have been given, could have been supplied as the ROC for xz. Briefly, suppose xz had been the same, but we had been told that the ROC was r greater than 2. Suppose we were told that the ROC was r greater than 2. Now, is it possible to have an ROC which is r greater than 2 for an expression like this? It is not possible to have an ROC for r greater than 2, because remember that xz equals 1 by 1 minus 2z inverse plus 1 by 1 minus 5z inverse. Now, if you have an outward ROC, that outward ROC would be the intersection of two outward ROCs. An outward ROC must be the result of intersection of both outward ROCs. But if you produce an outward ROC from the first term x1 of s, x1 of z, that will be outward from 2. The second term will produce an ROC which is outward from 5, and the intersection of these two will only be outward from 5. It will not be outward from 2. Hence, this specification is incorrect. There can be no signal x n which has this given xz as the algebraic expression and an outward ROC starting from 2. However, if we had been told that the outward ROC was starting from 5, that is to say x z with r greater than 5, then clearly we would assign our outward ROCs to both these terms, and we would get xn, if I may be allowed to write it right away, as 2 to the power n un plus 5 to the power n un. Both right sided signals, both outward ROCs, and hence the overall ROC is the intersection of two outward ROCs, hence it is outward from 5, from mod z equal to 5, right. Now, suppose we had both inward ROCs, that is the next possibility. So, we will call this possibility A and we will look at possibility B. Suppose we had been told inward ROC starting from 5. This is also an impossible case, because an inward ROC can be the result only of intersecting two inward ROCs, and when you have two inward ROCs, the inward ROC that x1 can give is inward from 2, x2 can give an inward ROC starting from r equal to 5, that is r less than 5. The intersection of these two will only consist of an ROC starting an ROC for r less than 2. It will not consist of r less than 5. Hence, this specification is incorrect. However, if we had said inward ROC r less than 2, then that is fine, because we would have said that we have two sequences, both left sided sequences, and we would write x n equals minus 2 to the n u minus n minus 1 minus 5 to the n u minus n minus 1. This is fine. This is perfectly acceptable. There is only one last possibility, which we will call as possibility C. This possibility C is not actually a possibility, it should be called an impossibility. C. What if x1 of s had an inward ROC and x2 of s had an outward ROC? Then we would have been told that ROC is null. Interestingly and almost humorously, even when we are told that the Z transform does not exist effectively, so long as we are given the expression which was given to us, namely the expression of the Z transform is 2z square minus 7z by z square minus 7z plus 10. If you are just given this expression, then I mean given this expression as well as told that the ROC is null, we can still invert it. We need an inward ROC for x1s and an outward ROC for x2s. That means a left sided sequence for x1s, a right sided sequence for x2s. So you would get xn equals minus 2 to the n u minus n minus 1 minus plus 5 to the n u n. This sequence will not have a Laplace Z transform for any value of r. That means it will converge at no point on the Z plane. So that was a thorough workout of one example. We have beaten it from all directions and seen what comes and what